Alright, so today we're going to be looking at the mole and how it's used in chemistry. So the mole is going to be relatively similar to a dozen, just instead of being 12, it's going to be something bigger. So again, if we have a dozen of something, we know that there are 12 of those somethings, whether it's eggs, donuts, whatever. If I say I have a dozen of these, I know that there are going to be 12 of them. And the mole is going to work on the same concept, except that a mole is going to be much, much bigger than 12. So if I have a mole of something, and whenever I'm talking about moles, I'm going to be talking about atoms or molecules because literally anything else would just be too astronomically large to deal with in terms of a mole. But one mole is going to be equal to 6.02 times 10 to the 23rd atoms or molecules. And taken out of scientific notation, you can see how big that number is. It's massive. So this is, again, why we wanted to make sure that we got scientific notation down before here so that you have an idea of how big a mole actually is. And then this is also known as Avogadro's number. So anytime you hear Avogadro's number, you're going to think 6.02 times 10 to the 23rd. You don't have to necessarily remember these next couple slides, but they're just an idea for you to get of how big a mole actually is, like how big that number is. So if atoms were the size of marbles, and I had 1 mole of marbles spread over the entire surface of the Earth, the planet would be covered by a 50-mile thick layer. So the entire surface of the Earth covered in 1 mole of marbles, that layer would be 50 miles thick. That is absolutely massive. And that's just, and if you think like a mole of molecules is actually something really, really small, like we're talking maybe like a box yay big or so, would have a mole of atoms. So it's kind of a combination of how big a mole is and how small atoms are. Also, if we made $40,000 or the equivalent of 4 million pennies, and you made that every second at a job that you've been working at since the formation of the Earth 4.5 billion years ago, you still wouldn't have earned an Avogadro's number worth of pennies. So you still wouldn't have a mole's worth of pennies, even if it's $40,000 a second for 4.5 billion years. It's an absolutely massive, massive number. Okay, so before we can start doing stuff with moles, we need to know about what's called molar mass. So this is going to be defined as the mass of 1 mole of the substance. So whatever substance it is we're looking at, if I have 1 mole of it, that's how much mass that that substance would have. And so we calculate that by adding the atom's mass off the periodic table. So again, we're going to be using the periodic table here, and we use the atomic masses to figure that out. The atomic masses and molar masses are basically the same, and that's essentially how we came up with a mole, was to basically make life a lot easier. The units for this are going to be grams per mole. This is super important that you know it's grams per mole. A lot of students, for whatever reason, don't remember that it's grams per mole. So please make sure, anytime you see molar mass, the units are automatically going to be grams per mole every single time. Okay, so looking at how much do certain things weigh. So we're going to look at the periodic table for this. So 1 mole of oxygen. So if I pull up the periodic table and I look at oxygen, I can see that it's 15.999 or 16.0 on your periodic table. So 1 mole of oxygen is actually going to be 16 grams because it's just 1 mole is whatever the atomic mass is on the periodic table. If I have 1 mole of sodium, so again, if we go to check the periodic table, find sodium, 22.99, we'll round it to 22.99. So if I have 1 mole of it, it's going to occupy 22.99 grams. If I have 2 moles of carbon, so again, going back to the periodic table, if we find carbon, so 1 mole of carbon I know would be 12.01 grams per mole, or the mass of 1 mole would be 12.01 grams. But if I have 2 moles of it, or I have basically 2 of them, it's going to be 12.01 times 2, so 24.02. 3 moles of hydrogen. So again, looking at the periodic table, hydrogen's mass is 1.01. So if we have 3 of them, then spoiler alert, it's going to be 3.03. So you just simply have, if you have more, something that's not 1, so whether it's more or less, it doesn't matter which way, all you have to do is just simply multiply the atomic mass on the periodic table by however many moles of the thing you have, and that's how many grams that sample would weigh. Now 1 mole of H2O. So if we look at H2O, or water, that 2 in the subscript here, or where it's down low, that anytime that it's down low, it applies to whatever is directly to the left. So immediately, whatever's left of it. So in this case, that's going to be the H. So that means that I'm going to have 2 H's, and then I'm going to have 1 oxygen. So oxygen, looking at the table, is 16.00. Hydrogen is 1.01. So if I look at each of them together, for my hydrogen, if I've got 1.01 times 2, that's going to be 2.02, plus my 16, because I've got to remember that. So 2.02 plus 16 is 18.02. That's all there is to figuring out how many grams are in a certain amount of moles of something. And that's also how you figure out the molar mass. It's just simply looking at the periodic table. Whatever the number on the table is going to be the molar mass of that substance. Okay, so example time. And you'll definitely want your periodic table out for this because I'm not going to keep bumping back and forth between these. Okay, so I want to figure out the mass, or the molar mass, of ammonium sulfate. And then anytime you have a subscript outside of a parentheses, like we have this 2 here, remember the subscript is always going to apply whatever's directly to the left. And so in this case, that's the parentheses. So that means that I'm going to have 2 of everything in the parentheses, or if whenever I go to do the math, I essentially multiply all of those values by 2. So what you're going to want to do is set up a just a quick table. And as you get better at this, you may be able to skip over this step, but especially when we have more complicated things, like this is a real big molecule here. We've got 4 different elements in there, and then there's numbers all over the place. So even when you get good, I would recommend still, if you're to err on the side of caution, take the extra minute it takes to set up one of these tables to figure that out. But basically what I'm going to do is I'm going to have a column for the symbols, the atomic mass, the number of atoms, and then the total masses there. So the symbol, we'll go ahead and get those down. So the symbol is going to be the elements within the sample, or basically the atomic symbol of the stuff. So I can see I've got nitrogen in there. I also have hydrogen, I have sulfur, and I have oxygen. Okay, so next up, I'm going to bold this just to make sure everything's clear. Okay, so next up we put the atomic masses of the elements. I'm not counting like how many of each thing I have right now, I'm just simply looking at the periodic table. So nitrogen is 14.01, hydrogen is 1.01, sulfur is going to be 32.06, and oxygen is 16.00. Okay, then the number of atoms. So I'm going to look at my thing and figure out how many of each atom there are. So normally there would only be 1 nitrogen, but it's within these parentheses, and there's a 2 outside of them. So 1 multiplied by 2 means that I have 2 atoms of nitrogen. For hydrogen, that's going to be, so normally I would have 4, but I have to multiply by 2 because it's inside those parentheses. So I'm going to have a total of 8 hydrogen. Sulfur, there's only 1. There's no subscript to the right of sulfur, and it's not inside of any parentheses, so that's just 1. And then oxygen, I can see I've got 4 of them. Now I've got it set up so it already did the math for me, but then you would take your atomic mass, multiply by the number of atoms, which is basically what we just did on the last slide, to get your total mass for each thing. So I know nitrogen is going to have a total of 28.02 in it, 8.08 for hydrogen, 32.06 for sulfur, and 64 for oxygen. Once you have all of those things together, then you're just going to simply add them up. And I'm going to cheat and use Excel to do this. But you would just do 28.02 plus 8.08 plus 32.06 plus 64. And when you do that, you get 132.16. And remember, we always need to have units. And the units for molar mass are grams per mole. So the molar mass of ammonium sulfate is going to be 132.16 grams per mole. All right, so go ahead and try barium acetate on your own real quick. And then I'll go through it. So if you want to go ahead and pause real quick, try it on your own. Okay, so we're going to go through the same process. We want to make sure we set up our table where we have our atomic symbol, our atomic mass, the number of atoms, then total masses, and then remember we'll add them up when everything is all said and done. So for my symbols, I have barium, I have carbon, hydrogen, and oxygen. Okay, so looking at my atomic masses, so for barium, let's see, find it on the periodic table, that's number 56. So that's going to be 137.33, I believe. Carbon, it's going to have a mass of 12.01. Hydrogen, 1.01 again. And oxygen is going to be 16.00. By the way, a lot of these common ones like carbon, hydrogen, and oxygen, you're going to have those memorized just from doing this so many times with them. So you're going to get to the point where you don't have to use the periodic table for every single one of these. It's just going to be ingrained in your head. Okay, barium, I have one of them. Carbon, so normally I would have just had 2 of them, but it's inside of parentheses with the 2 on the outside, so I'm going to have 4. Same sort of thing with hydrogen. I was going to have 3, now I've got 6. And then oxygen goes from 2 to 4. Then of course we add them all up together. So 137.33 plus 48.04 plus 6.06 plus 64, and we get 255.43 grams per mole. Always, always, always remember your units. Okay, so if you remember, 6.02 times 10 to the 23rd things is equal to 1 mole of something, because that was what Avogadro's number is. And we also know that 1 mole of something is equal to however many grams the mass on the periodic table says, which is what we just did. So we can create what I like to call your roadmap. And this is super important. It really needs to have its own page, or at least its own like half page, its own section, because you're going to be using this very, very heavily for a good long time. So make sure it gets plenty of space on your paper. So anytime that we want to convert between these units, we're going to use this roadmap. Kind of like how we set up roadmaps when we were doing dimensional analysis to begin with, where as you started with something and you ended with something, and we try to figure out what went in between. This is that already set up. So if I know that if I'm starting with grams and I'm trying to get to moles, I can go straight from grams to moles as long as I use molar mass in my conversion. If I'm trying to go from moles to atoms or molecules, I can do that, but I've got to use Avogadro's number. If I want to go from atoms or molecules all the way over to grams, I know that I have to go to moles first, so I have to do my train track from atoms, bring atoms back down, moles up top, and then I've got to go moles on bottom and then grams up top. But using this roadmap, it takes out a lot of the thinking that you would normally need to do. So make sure you have this somewhere it's easily accessible, and make sure that you memorize how to get from one thing to the other, because that's going to be incredibly important to do. So in the next video, we're going to talk about or go over some examples of just simply how to use it.